In this video, we will explore the discrete spectra and the models that predict them. At the dawn of the 19th century, it was discovered that a low-pressure gas, filling a glass bulb, glowed when an electric current passed through it. Actually, a first explanation was made in terms of classical electricity and magnetism, as developed by Faraday and Maxwell. But an unexpected result was the fact that the spectroscopic analysis of the light emitted by the glass bulb resulted in a set of discrete peaks that commonly are called spectral lines. This result was contrary of the black body radiation, in which the spectrum was a continuous set of wavelengths. As we studied in a previous video, the emission of hydrogen was of vital importance, as it was the simplest spectrum. A few very well-defined lines in the visible range. Also, larger atoms in the periodic table could be approached to a larger version of the hydrogen atom. Absorption of hydrogen was also an important phenomenon to be explained, as only specific lines were missing when the light of a white source passes through a glass bulb filled with the gas. Let's review what the experimental setups were. For the case of the hydrogen emission, the radiation generated was passed through a slit to reduce the size of the beam. Then it passed through a prism to separate its components, and finally projected in a screen. Years later, the use of photographic plates became popular. A similar scheme was used to study the black body radiation. On the other hand, for the hydrogen absorption, a white light source was used to illuminate a low-pressure bulb. The prism and the screen or photographic plate were used as in the previous cases. An empirical model was proposed by Johann Balmer in 1885. This model allowed the prediction of the hydrogen spectral lines. The series of emission lines given by the Balmer formula is called the Balmer series for hydrogen. And the model has the following expression, where n is an integer number larger than 2. It refers to the order of the spectral line position. And r, h, is a constant. Let's solve an example to see how the Balmer series work. Example 12. Determine the first 5 spectral lines of hydrogen by using the Balmer model. Could you solve it? Answer. We know that the Balmer series has the following form. As we want the first 5 spectral lines, then we need to use the following values of n. Substituting these values on the Balmer series, we get the following. Finally, the resulting wavelengths are these. As a practice check, what colors do these wavelengths represent? Actually, we have showed these colors before, in the emission spectrum. A few years later, Johannes Rydberg proposed a model that predicted all the spectral lines of hydrogen. The expression of the so-called Rydberg series is the following, where r, h, has the same value than before, and actually is called the Rydberg constant. Also, n, I, and n, f, are related in the following way. This model was very important because it reproduced the Balmer series, but also predicted other series that eventually were measured. A summary of the predicted series by the Rydberg formula are the following. Notice the value of n, f, in each case. A graphic representation of the wavelengths of each of the series mentioned before is the following. Notice that the name of each spectra is simply the first two letters of the series name followed by alpha. In a future video, we will explore the meaning of alpha. Finally, it is important to see that the wavelengths in the horizontal axis are represented in a logarithmic scale. Furthermore, the hydrogen emission spectrum is not limited to the visible range. Actually, there are several regions of the electromagnetic spectrum, ranging from the ultraviolet to the infrared. In the next video, we will explore the atomic model that allowed the understanding of this discrete spectrum and its consequences in the modern physics revolution. Stay tuned.